Just a couple of announcements before we get started. As a reminder, you have your first chunk of ALEX topics due tonight. That is the angles and radians assignment. It's the first one. There's 7 topics. Many of you have already done this. If so, thank you. Beautiful, you're good to go. If not, just a reminder to sign into ALEX and complete those before the end of the night. And then the next assignment, which I believe is right triangle and circular trigonometry, will open immediately after that, and you'll have a few days to do that one. As well, your first written homework is due tomorrow night at midnight. That will just be print out the homework that is a PDF right now in your Wild Course shell, write it out, and then rescan and upload it as a PDF. Again, there's a lot of apps out there. I think Cam Scanner is one of the good ones where you can just snap a picture of it and immediately converts it to a PDF, and you can even upload it to Wild Courses through there. But whatever method you use works. Are there any questions on anything logistically or otherwise? Okay, then if there's no questions, we will hop right back into what we were doing yesterday, which was working with the 6 trig functions. So let me share the slideshow. Okay. So this is where we left off yesterday, I believe, which was defining all 6 trig functions. We worked a lot yesterday with cosine and sine, which is just the x value over the radius or the y value over the radius. We worked a ton with those. We also talked about tangent and how tangent is just y over x, which ends up just being sine over cosine because those radii in the denominator cancel. So tangent works really nicely. But the new ones we're going to talk today, and that I briefly defined yesterday, are secant, cosecant, and cotangent. And essentially, these are the inverses of the first 3. We call them reciprocal functions. And their reciprocal just means we take a fraction and we flip it upside down. That's all a reciprocal is. So that's why these are reciprocal functions. Secant is the inverse of cosine. It's 1 over the cosine, or we can just think about taking x over r and flipping it into r over x. Cosecant is the inverse of sine, so we can just flip y over r into r over y, or just 1 over sine if you're given the value for sine. Cotangent, instead of y over x, which is the slope as we talked about, it's just x over y. Okay, so let's get some practice using these a little bit more. So let theta be an angle in quadrant 4 such that the cosine of theta is 7/9. That's all we know. And we want to use this information to find the cosecant and the cotangent. Before we do anything, I'm just going to write down what the formulas for cosecant and cotangent are so we can remember what information we're looking for. We know that the cosecant of theta is the inverse of sine, so it is r over y. And we know that the cotangent of theta is the inverse of tangent, or the reciprocal of tangent. So this is just x over y. Okay, so we're going to need all 3 of these pieces of information, x, y, and r. Okay, so let's draw theta, because drawing a picture is honestly, I think, one of the best ways to approach these problems, help us get our information straight in our head. Here's our axes, and theta is in the 4th quadrant. And if you remember the quadrants, this is 1, and then we just go counterclockwise around 2, 3, and 4. So this is quadrant 4 down here. So we have some angle theta. We don't know how we got to theta. We could have started with our initial right here and gone all the way around like this. It could have been a negative angle where we went down like this. We could have done a loop-de-loop 5 times and somehow still landed at this ray. It does not matter how we got to this ray. All of the values of the trigonometric functions be the same. Okay. And we know that the cosine of theta is 7/9. But also recall that the cosine is the adjacent side over the hypotenuse, which in graphing language is x over r. So it turns out we already actually know some information. We know that the ratio of our x to our r is 7/9, so we can just use that here. We can say that r is 9, and that our x, this side of the triangle right here that we're creating, is 7. So all we're missing right here is this guy. I'll call it B. And again, we have a right triangle with two sides known. How do we solve for the unknown side? Pythagorean theorem. So let's do that. So to solve for B, we can do 7 squared, one of the sides, plus the other shorter side, which we don't know what it is, so it's B squared, is equal to 9 squared. Doing some arithmetic, 49 plus B squared is equal to 81. Some more arithmetic, by subtracting 49 from both sides, we get that B squared is equal to 32, and therefore B is equal to plus or minus the square root of 32. We don't know which plus or minus it is yet. We'll talk about that in a second. However, 32 is not quite in its full simplified form. There is still a perfect square we can pull out of 32, because if you notice, 32 is equal to 16 times 2, and 16 is a perfect square. So we really like that, because once we have this, we can say it's equal to plus or minus the square root of 16 times the square root of 2. Square roots are nice that way. We can break up multiplication like that. Remember, we cannot break up addition under a square root, but multiplication we can break up. Square root of 16 we know is 4, and then just leave it as square root of 2. So this is our final simplified answer of the number. However, is it positive 4 square root of 2 or negative 4 square root of 2? Well, that's where the information of what quadrant we're in comes into play. The cosine of theta could be 7/9 in either this quadrant down here, or it could have been 7/9 in quadrant 1. However, because we know we're in quadrant 4, we can see that we have a negative y value. We have a positive x value and a positive radius, because the radius is always positive. However, we have a negative y value because we are going down to the negative part of the y-axis. So it turns out the answer is negative 4 square root of 2. Does that make sense? Are there any questions on how I made that deduction? Okay. All right, so we know that B is negative 4 square root of 2. And we can use that and now just use these values with our two formulas for cotangent and not cosine, cosecant, to figure out the information we need. So cosecant of theta is equal to r over y. We know that r is 9. And we know that y, as we just solved for, is negative 4 square root of 2. And this is technically correct. However, as was brought up yesterday, radicals or square roots in the denominator are disgusting. We don't like them there. The reason for this is it's kind of mathematical convention, and it's just much easier to not have to divide by things with a square root. So in mathematics, and especially if you go forward to take calculus, you will need to know how to get the square root out of the denominator. So we're just going to do some practice with that now. So I'm going to do something called rationalize the denominator. And that is just multiplying this entire thing by a fancy 1. I don't want a root 2 in the denominator anymore. And how do I get the square root of 2 to not be a square root of 2? I can multiply it by another square root of 2. Remember, root 2 over root 2 is just a really fancy way of saying 1. However, because I'm multiplying the square in the denominator by itself, it's going to go away. Because when I do that cross multiplication, I will get 9 root 2 in the numerator. And then the denominator, I will get negative 4 times square root of 2 times square root of 2. And square root of 2 times square root of 2 is just 2. So my final answer is 9 root 2 over 8, and I'll just put the negative up in the numerator because it looks nicer that way. Does it make sense how I did that? And again, we'll get more practice with rationalizing the denominator a lot, especially today. So if that didn't make sense the first time, we are going to keep getting more practice with it. Okay. So now we just want to find the cotangent, which is a really similar process. Just using our formula for cotangent of theta, it is x over y. So it is 7 over negative 4 root 2. Again, this is technically correct, but we don't like that nasty root 2 in the denominator. So I am going to multiply this expression by the fancy 1 of root 2 over 2 to get rid of that root 2 in the denominator. Numerator, we're landed with 7 root 2. Denominator, we have -4 times 8, or times 2 again. So our final answer is -7 square root of 2 over 8. Any questions on this example at all? Okay, then let's do another one. Let 7, -3 be a point on the terminal side of theta. Find the sine, cosecant, and cotangent. Okay, so just as a reminder, because I like to have these formulas to look at when I'm working through these, I know that the sine of theta is the y-coordinate over the radius. Cosecant of theta is the inverse of sine, so it's just the radius over the y-coordinate. And cotangent of theta is the inverse of tangent, so it's just the x-coordinate over the y-coordinate. Okay, so let's draw a picture. I know I've used the word terminal a lot. Just remember that when we talk about an angle, we have two sides. We have the initial side, which in almost all cases for us has been lying on the positive x-axis right here. And we have what's called the terminal side. It's where the angle terminates. It's where it ends. That's why it's called the terminal side. It's the only other side it could be, pretty much. So we have our initial on the positive x-axis, and then we know 7, -3 is a point on the terminal side of theta. So it's +7 and then -3. So we know that that's where that lies. And then here we have the terminal side of theta, and that passes through this point. Okay, so we want the sine, cosecant, and cotangent. Well, what do we know? Because we're given the x and y coordinate, we already know two sides of this triangle already. We know that this side here has a length of -3, and that this side here on the x-axis has a length of 7 because we're going across 7 and down 3. Well, how do we find a third side in a right triangle when we're given two sides? Pythagorean theorem. So this time we actually have the two short sides. We have 7 squared plus 3 squared, and we're solving for our radius. 7 squared is 49, plus 9 equals r squared. 49 plus 9 is 58. So we have that our radius equals plus or minus the square root of 58. Radii will always be positive. When we're talking about the hypotenuse, we never even have to consider the negative case. So it is positive square root of 58. And there's no further way to simplify this. There's no other way to pull a perfect square out of 58. So I'm just going to leave that be. And now we actually have all the information we need to do this problem. So like last time, let's set it up with sine of theta is equal to y over r. Our y coordinate is -3. Our radius is the square root of 58. We don't like square root of 58 in our denominator because square roots and denominators are a no-no. We don't do it in math. It's not allowed. So we need to rationalize again. To do that, and this time we want to get the square root of 58 out of there. So our fancy one will be a square root of 58 over square root of 58 because we know that that will make the square root of 58 go away. And that is equal to -3 times the square root of 58 over 58. Because square root of 58 times square root of 58 is 58. Okay, now move on to the cosecant of theta. Similar process, we know the radius is square root of 58 over our y value. We're just basically inverting our other answer. And that's it. That's all we have to do for that one. The square root's in the numerator where we like it. It's happy up there. So we don't need to do any rationalization. We have our final answer. That's it, just r over y. Lastly, cotangent of theta is equal to x over y. Our x value is 7 across, and our y value is -3. And that is it for that one. There's no square roots in there to even think about dealing with. We have a really nice answer for cotangent. Any questions on how we did this problem? Okay, let's try a different kind of example then. Similar idea, just using some different skills. Let theta be an angle in quadrant 2 such that the tangent is a -4/3. Find cosine and cosecant. Let's set this up like we have been. The cosine of theta, what we're solving for, we know is the x value over the radius. And the cosecant of theta, which is the inverse of sine, is r over the y value. Drawing our picture, we know that our angle is in quadrant 2 and the tangent is -4/3. So we know the tangent of theta is -4/3, and we know that tangent is y over x. So we can say, we know that the terminal side of our angle here passes through the point x equals 3, y equals -4. Or is it, sorry, my bad. We know that there is a point over here that the terminal side passes through that is x equals something 3 and y equals something 4. I put the positive, or I put the negative sign in the numerator because it's convention. However, I misspoke because it is not x equals 3, y equals -4, because if it was x equals 3, y equals -4, our x value would be positive, but our y value would be negative. So that would land it in quadrant 4. However, we're given that it's in quadrant 2. So we know that one of these two values must be negative, the 4 or the 3. And because it's in quadrant 2, we know that the x value must be negative. So this point is actually -3, 4. You should always do that check in your head, because when it gives you the quadrant and the tangent, you know that, okay, if the tangent's positive, if say I gave you tangent if theta was +4/3, you knew that either both the x and the y were positive or both the x and the y were negative. If the tangent is negative, like in this case, you know one of the x or y is negative, and you have to use the information about which quadrant to figure out which it is. Okay, so we know it passes through that point here. So we have an unknown radius, but we know we've created a triangle with a x value that has length 3 and a y value that has length 4. So using the Pythagorean theorem again, we can solve for r. 3 squared plus 4 squared equals r squared, which is 9 plus 4 squared is 16, is r squared. 9 plus 16 is 25 is r squared. And so r nicely is actually 5, because the square root of 25 is 5. This is one of the nicest triangles you'll ever see. It's called the 3, 4, 5 triangle. It's beautiful. So we can label this guy up here as being 5. And we know it's +5. I skipped over the part where we have to decide whether it's a plus or minus square root of 25. It's positive because we're talking about a radius. And again, now we have all the information we need to complete the problem. We want the cosine of theta, which is x over r. We know that x is -3 and the radius is 5. And then the cosecant of theta is the radius over y. The radius is 5 and the y value is a +4. Any questions on this one? How we needed to use the quadrant and the sign of tangent to deduce which value, the x value or the y value, is positive or negative. Sometimes you'll be given ratios like that are positive or negative and a quadrant, and you will get to use that information to decide what the values are and which one's positive or negative. Okay, so let's do a bit of a different example with these kinds of quadrants. In other words, determining which quadrant they lie in given certain information. So we want to determine which quadrant the terminal side of our angle theta lies if both the sine of theta is less than 0, so negative, and the tangent of theta is less than 0. So how I like to approach these is I like to just focus on one thing at a time. So I say, okay, what if we just know the sine is 0? What quadrant could it be in? And then, okay, what if we just know that the tangent is negative? What quadrant could it lie in? Okay, so just to draw a bit of what I think is a helpful diagram, here's quadrant 1, 2, 3, and 4. we know that if we have any point here in quadrant 1, it is going to be a positive x value and a positive y value because we're on the positive sides of both axes. If we have a point in quadrant 2, we are going to have a negative x value and a positive y value because we're still in the positive y's, but we move to negative x's. All points in quadrant 3 will have a negative x value and a negative y value. And then all points in quadrant 4 will have a positive x value and a negative y value. So let's focus on this guy first, the sine of theta being less than 0. We know that if the sine of theta is negative, that means the y value is negative because the radius is always positive and sine is y over r. So the sine is entirely dependent on what the y value is. Which quadrants are the y values negative? The third quadrant and the fourth quadrant. So the sine of theta being less than 0 can happen in the third quadrant and the fourth quadrant. Okay, now let's just focus on this piece of information. When is the tangent of theta less than 0? I talked about this a little bit on the last slide with how this came up with our negative tangent here. But this happens when we have our x and our y values being of opposite signs, because if you remember, a positive divided by a positive is positive. A positive divided by a negative is negative. A negative divided by a negative is positive. And a negative divided by a positive is a negative. And y divided by x is how we find tangent. So we want to look at the signs of those 4 divisions there. So when is tangent negative? It's when the signs of the x and y value are opposite, which happens in the second and the fourth quadrant. Okay, now let's put this all together. We know that both of these things must be true simultaneously. So sine is less than 0 in the third quadrant, but the tangent is not less than 0 in the third quadrant, so it can't be the third quadrant. We know that the tangent is less than 0 in the second quadrant, but the sine is not less than 0, so it's not the second quadrant. The only quadrant these two have in common is the fourth quadrant, so our answer is quadrant 4. Does that make sense, how I got to that answer? Are there any questions? Okay, then let's try a similar example. We know that the cosine is negative, but the sine is positive. For cosine being negative, we just look where the x value is negative because the sign of the x value determines the sign of the cosine. If we look, the cosine is the quadrants on the negative x-axis. So this occurs in quadrants 2 and 3 because those are the 2 quadrants where the x value is negative. And then the sign being positive happens on the sides of the axis where the y values are positive. So those upper 2 quadrants, which are quadrants 1 and 2. Cosine is negative in quadrant 3, but the sign is not positive, so it can't be quadrant 3. The sign is positive in quadrant 1, but the cosine is not negative, so it's not quadrant 1. The only one these guys have in common is quadrant 2, so your final answer is quadrant 2. Any questions on how we deduced this? You can kind of think of these problems as puzzles, sort of, just using all the information you know about trig functions where things are positive and negative, kind of a process of elimination, deducing, okay, what do I know? What do I know? What do these have in common, etc. Okay. Well, if there aren't any more questions on this one, we will, one second. Let's move on to another example. Okay, so we have an angle theta with the cotangent being -7/5 and a secant less than 0. And we want to find the sine of theta. Well, let's do a similar analysis to what we did up here on the previous slide. Let's ignore the fact that the cotangent is -7/5 right now and just focus on the fact that the cotangent of theta is less than 0. Because again, that's the same thing as what this is saying. It's actually just less specific information because -7/5 is less than 0. So let's focus on that. What quadrant is the cotangent negative in? Well, just like tangent, the cotangent is a ratio of x's to y's. So the cotangent will be negative when x and y have opposite signs, just like tangent above. And from what we did here with this division, we know that the cotangent is negative precisely in quadrants 2 and 4. So let's make a note of that, because we're trying to figure out which quadrant our angle's in so we can draw it. Okay, so just based on this little piece of information here, we've narrowed down 2 quadrants our angle could be in. Let's use this third piece of information to figure out which quadrant it's in. Okay, so if we recall, the secant of theta is the inverse of cosine, so it is r over x. As such, the x value, or the sign of the x value in particular, determines when our secant is positive or negative. It determines the sign of the secant. And I don't mean sign as in the sine function, I mean sign as in S-I-G-N, the positive or negative sign. So we just need to look, okay, we want secant to be negative. In which 2 quadrants are x values negative? Quadrant 2 and quadrant 3. Now, from these 2 answers, which quadrant do those 2 have in common? Quadrant 2. So we know that our angle lies in quadrant 2, and we have some of its dimensions already, so we are able to sketch it. Okay, so we have this guy here. We know the angle is in quadrant 2, and here's a point, and we know that point is -7 because we are going in the negative x direction because we are lying in quadrant 2, comma 5. And I know this because remember, cotangent is x over y, so the x equals 7 and the y equals 5, or -7. Okay, so we've constructed this triangle that has one side length of 7, one side length of 5, and because we are looking for the sine of theta, which is the y value over the radius, we need the radius in order to complete the problem. So let's slap it with the Pythagorean theorem again to get our radius. We get that 7 squared plus 5 squared is equal to r squared, which is 49, which is 7 squared plus 25. 5 squared equals r squared. 49 plus 25 is 74. So r is the square root of 74. I can't simplify this any further. There are no perfect squares I can pull out of 74, so I will leave it as is. And then we can just solve for the sine of theta. Sine of theta is y over r, so our y value is a +5 because we are in quadrant 2 going in the positive y direction, over our r, which is square root of 74. Again, the square root is in the denominator, which is a no-no, so we're going to get it out of there by rationalizing, and to do that, we just multiply both the numerator and denominator by the square root we are trying to get rid of. So numerator, we get 5 times the square root of 74 over 74. And that is our final answer. Are there any questions on how I did this one? Okay, let's do another example. Because it never hurts just to get as many tools as you can under your belt. So when you're practicing these on your own, you have a bunch of different examples and techniques we used to reference. Okay, let theta be an angle in quadrant 2 such that the secant of theta is -17 over 15. Find the sine and the cotangent. Now this one's not so bad. We're already given the quadrant, so we don't have to do this analysis again that we did up here. We just already know where to draw our angle, which is really convenient. Okay, so drawing a set of axes, angles in quadrant 2, and we know that the secant of theta is -17 over 15, and secant, if you remember, is the inverse of cosine, so it is r over x. Well, we actually don't even really have to think too hard about which of these two is negative, because as we've discussed, the radius will never, never, never be negative. So the 17 is oops, the 17 is the positive value. And so we have a negative 15 in the x direction here. This will be length 15, but it's in the negative direction. And that matches up because we're in the second quadrant where the x's are negative. Okay. So we now know that this point here is negative 15 comma some y. Again, we want to find the sine of theta, which is y over r, and the cotangent of theta, which is x over y. So we need this y value. So to solve for it, we're going to plug these things into Pythagorean theorem and solve. We get that 15 squared, our known side length, plus y squared, we're solving for y, is 17 squared. 15 squared is 225 plus b squared, or not b squared, y squared, called it y, is equal to 17 squared, which is 289. We subtract 225 from both sides. It turns out that 289 minus 225 is 64. And the square root of 64 is 8. So we know we're in quadrant 2, which means we have a positive y value. So it is positive 8. This side length here is 8, and this y value is 8. That point is negative 15 comma 8. We now have all the information we need. Sine of theta is the y coordinate 8 over the hypotenuse 17, or the radius. And the cotangent of theta is the x value over the y value. X is negative 15 and y is 8. Any questions? Okay. So let's get another tool under our belt and learn another piece of vocabulary. And that is about something called a reference angle. So the reference angle of an angle theta in standard position is the acute angle, so it will be less than 90 degrees, formed by the terminal side of theta and the x-axis. Now that may sound somewhat confusing, but it's not as bad as it seems. Let me draw a couple pictures real quick. So here's some axes. And let's say this guy right here is our angle theta. That was very bad. I'll try that again. Here's angle theta. I'm going to call this guy theta. So the reference angle would be the angle formed between the terminal side, which is that guy there, and the x-axis, the closest x-axis. So the reference angle for this guy here, we would just go down this direction. We'll call it theta prime. That little hash mark I put above theta is called a prime. We'll just call it theta prime. Theta here is our initial angle, and theta prime would be the reference angle. As another example, let's consider this angle here. And let's say that this is theta. Let's say we went all the way around there to make theta. Our reference angle, theta prime, would be this guy here. We're taking the terminal side, forming it to the x-axis, and that is our reference angle. Notice that this will always, 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 always be less than 90 degrees, because if I could make it bigger. Here, I could make this one bigger. This angle could end here and it would be closer to 90 degrees. It could end here and then be even closer. But the second we'd cross over the y-axis, we would then form the reference angle with this x-axis. We wouldn't go over here to make an angle greater than 90 degrees. It would go here. So the reference angle will always, always, always be less than 90 degrees. And that is actually the exact reason this is helpful. They are useful because the value of any trig function of theta is equal to the value of that function of the reference angle, maybe give or take the sign. And what I mean by that is essentially all of the information you will need in order to evaluate some functions, you will know just by memorizing the first quadrant of the unit circle. You don't need to know all 4 quadrants because it turns out they're all actually really similar. If you've looked at it or studied it at all, there's a lot of similarities. So all you will need to know is the value of the reference angle And then that gives you the sine, cosine, tangent, et cetera, of much larger angles. The only difference being you will have to consider what sign the answer will be in based on what quadrant the angle lies in, because everything in the first quadrant will be positive. But it's an extremely valuable tool. So let's do some examples just to see how it works. We want the reference angle for 7 pi 12ths. We're not doing anything, we just want to find the reference angle. So I'm a visual learner. I like to see pictures. Let's draw a picture. Now, first of all, which quadrant does 7 pi 12ths lie in? Well, from the unit circle, an entire revolution is 2 pi radians, right? So half of a revolution is pi radians and a quarter of a revolution is pi halves radians. Turns out pi over 2 is equal to 6 pi 12ths, just a less simplified version of pi over 2. And this guy is slightly bigger than pi over 2, but is clearly not a full pi yet. It's not 12 pi 12ths. So we know that we're lying in the second quadrant somewhere. We know that our theta, our 7 pi 12ths, is somewhere in quadrant 2. Okay, so then visually, what does this mean? This means that our reference angle is whatever the value, whatever the value of this guy is right here. So how would we solve for this? Well, notice that theta and theta prime are supplementary. Their sum will be 180 degrees, or in other words, their sum will be pi radians, because if you remember this conversion factor from the first day of class, that is how we do that conversion. So, hello.
Wouldn't 7 pi 12ths be in quadrant 3, not 2?
It would not be in quadrant 3, because everything in quadrant 3, if this here is pi radians, do you agree?
Yeah.
Okay, so things in quadrant 3 would be larger than pi. And this is not quite a.
Yeah.
That makes sense?
Yeah.
Oh, thank you for asking.
Yeah.
Okay, so does that make sense? Okay. So we know that pi or theta and theta prime are supplementary, so their sum has to be pi radians. So in order to solve for what theta prime is, we know that we can take pi minus 7 pi 12ths, because we have a full pi here and we want to subtract 7 pi 12ths, because we know that 7 pi 12ths plus whatever theta prime is equal to pi. So subtracting that pi from both sides, we get, or subtracting 7/12 from both sides, we get pi minus 7/12 equals theta prime. I'll erase this guy here just to make more room. Pi is actually 12 pi 12ths, just fancy way of writing it. Or not, yeah, pi is 12 pi 12ths because you can cancel the 12s. I'm just making a common denominator. Minus 7 pi 12ths equals 5 pi 12ths. So our reference angle here is 5 pi 12ths. Does that make sense? Are there any questions? Okay, let's do another one. Let's do the other one in radians, negative 28 pi 9ths. Again, I would like to draw a picture for this one because that seems easiest. And this is a very big number. So what I'm going to do is think about walking around the circle in the clockwise direction because it's a negative angle until we land where we need to. We know that for every half circle we go around, we are going 9 pi 9ths because half of a circle is pi radians. So I'll just count that way. So here we're starting at our initial side. Here is 9 pi 9ths. 9 pi 9ths. Go around again, we get to 18 pi 9ths. We're not there yet. Negative 27 pi 9ths. Okay, we're almost there. And then we don't quite have enough pi 9ths to go over again. We only have one more pi 9th, so it's just barely over the axis here. And we're landing in 28 pi 9ths. So we're actually in the second quadrant again. So if you remember, when we were right here, we were at 27 pi 9ths. and we went up one more pi ninth to make it to negative 28 pi ninths. So our reference angle is formed right here by forming the terminal side with the x-axis. If we know the x-axis was 27 pi ninths, we go up one more pi ninth, we know that our reference angle is just pi ninths because it's 27 pi ninths plus one more. Does that make sense? You could also simplify this calculation without having to walk around like that if you wanted to. If you remember, these values for what we called coterminal angles will be exactly the same. So you could add 2 pi to negative 28 pi ninths to make the calculation a little bit easier if you wanted to, because it will have the same terminal side if we just add a multiple of 2 pi to it, which would be 18 pi ninths. That's just 2 pi. It's a really fancy way of writing 2 pi, which gets us to negative 10 pi ninths. So you could use that too, so you wouldn't have to walk around that much. Either way works if you want to simplify it first, or if you're okay with just thinking about walking around the circle in multiples of 9 until you end up where you need to. Either is okay. Okay, let's do that last example, which is in degrees. I'm going to erase this stuff on the right to do that because I'm running out of room. Okay, so negative 105 degrees. Let's just draw a picture because that's what we know how to do. So if we think about negative angles, they are going around in a clockwise, God, that's horrible. They're going around in a clockwise direction. So let's walk this way. That was negative 90 degrees. We're not quite there yet. We need to go a little bit more to negative 105. So we can say that this is our angle theta. It's negative 105 degrees. Now, just visually from this picture, we can see that the reference angle will be whatever this guy is. So again, theta and theta prime are supplementary. We know that the measure of theta, which is 105 degrees, it's negative 105, but we won't need it for cases of just solving for theta, plus whatever theta prime is, will be equal to 180 degrees. It's just another algebraic equation solving for one variable, which we can easily do by subtracting 105 from both sides. So we know that 180 minus 105 is equal to the measure of our reference angle theta prime. So theta prime is equal to 75 degrees. Any questions on how we got that? A lot of solving these will just be a process of intuition and thinking about, okay, where does my angle end? What does that mean for the reference angle? A lot of times it will just be thinking about that equation with supplementary angles, them summing to pi radians or 180 degrees, and then solving for the unknown reference angle. Sometimes in the case of this guy here, it is much easier just to think about drawing a picture because I don't know about you, but I don't know where negative 28 pi over 9 ends up just by looking at it. That's something I have to think through. Either way, drawing a picture is always extremely helpful so you can know how to attack these. Okay, let's see if we can use this a little bit to solve some problems. Just in evaluating these. Okay, I want the cotangent of negative 4 pi thirds. So drawing a picture up here, I know that theta here is negative 4 pi thirds, right? Because this is where theta goes. So the angle in consideration is negative 4 pi thirds. We go around this way, we're at negative 3 pi thirds and one more pi third. Up here is negative 4 pi thirds. Negative 4 pi thirds is kind of a nasty angle. I don't really want to think about it. It's not one that we use more commonly. What is one we use more commonly, though, however, is the reference angle. We know that this right here, the vertical axis is where we hit 3 pi thirds. We go one more up and we're at 4 pi thirds. So therefore, this reference angle right here, theta prime, is just pi thirds because it is pi thirds above the closest x-axis. So what does this mean? Well, it tells us that the cotangent of negative 4 pi thirds is the cotangent of pi thirds, give or take a sign. Like I mentioned on the last slide, the reference angle gives us the correct value. We just have to, once we are done with our computation, think about which sign is correct, because the reference angle will always have a positive sign because the X and the Y values are positive. So we have to think about, okay, is it the positive or the negative of it? But the value will still be the same, which is really convenient because I like pi thirds. Pi thirds is a lot easier to work with. So from our formulas, we know that the cotangent of any angle is X over Y, which also just happens to be the cosine of theta over the sine of theta. So the cotangent of pi thirds, we know, is equal to the cosine of pi thirds over the sine of pi thirds. And these are a couple of the first angles you will know from your unit circle and that you should be focusing on, because the first quadrant is extremely useful. I can't forget the plus or minus. So just from the unit circle alone, we know that the cosine of pi thirds is 1/2. And we know that the sine of pi thirds is √3/2. When we do fraction division, 1/2, invert and multiply 2 over √3, we get that this is 1 over √3, which again is technically correct. However, radicals, square roots in the denominator, can't do that, not allowed. So I'm going to multiply by the fancy 1 of √3 over √3 to get us to our final answer of square root 3 over 3, plus or minus. Okay, now we just have to think about which of those two signs it is. Is the cotangent positive or is the cotangent negative? Well, we're in the second quadrant, which means that our X value is negative and our Y value is positive. So when the ratio, when we divide the X value by the Y value, it's going to be negative. So our cotangent is going to be a negative √3 over 3 because that ratio of the X value to the Y value is negative. Any questions? Okay, let's do another one. Secant of 210 degrees. I want to draw a picture again because pictures are nice. I know it's more than 180 degrees because it's 210 is more than 180. So secant, we can draw that right here. This is a 210 degree angle. We know that the reference angle is 210 degrees, and we know that we went a certain amount over 180 degrees to get to 210. That is 30 degrees. So this angle here, our theta prime, happens to be 30 degrees. So that is the reference angle we can work with. In other words, the secant of 210 degrees, which is kind of a nasty number, is some variation of the sine of the secant of 30 degrees. And as on the unit circle, 30 degrees is one of our special angles. It happens in radians to be pi over 6. Looks a little more familiar. From our formulas, we remember that the secant, especially on the unit circle, is 1 over x, and x is the cosine. So we know we can solve for this by just finding 1 over the cosine of pi 6. Cosine of pi 6 is a special value from our unit circle, and we know that it just happens to be √3 over 2. Doing some arithmetic and dividing 1 by √3 over 2, we invert and multiply the bottom fraction. So we get that it is plus or minus 2 over √3. Again, I don't like that square root in the denominator, so I'm going to multiply by that fancy 1 of √3 over 3 to get rid of it. We have plus or minus 2 square root of 3 over 3. And now all we have to do is think about, is it positive or is it negative? Well, that is entirely determined by the sign of the cosine in the quadrant we are in, and the cosine is the X value. We are in the third quadrant. Everything in the third quadrant has a negative X value and a negative Y value. Therefore, the cosine is negative. So we are looking at a negative 2 √3 over 3. Okay, let's do one more real quick. I don't even think I want to draw a picture for this one because 360 degrees just goes all the way around the circle. So we don't really need to think about what that is because it's just the initial side is the same as the terminal side. However, using our formulas, we know that cosecant is 1 over y, which is the same as 1 over the sine of theta. So we can think about this being 1 over the sine, 360 degrees. If you think about the sine, aka the y value of the angle when it's lying on this positive x-axis, there is no height, there is no y value, it didn't go up at all. The y coordinate will be 0. And that is also a value you can verify on the unit circle. So the cosecant of 360 degrees is 1 over 0. That's not allowed. We're not allowed to divide by 0 in math. It's one of the greatest big, you cannot do this of math. So this cosecant of 360 degrees is actually undefined. We had another example like this at one point where we were looking at the tangent. If I believe it was pi halves, and we ended up having to divide by 0, so that didn't exist either. There will be times where you will end up dividing by 0, and as such, something will not exist. Are there any questions on how we did these? Okay, so let's look at some new types of arithmetic we can do with these sine and cosine functions and tangent functions and all the trig functions in general, just involving some factors of multiplication, both on the inside and the outside of the argument. Okay, let's say that theta is pi thirds. It's a nice, easy angle to work with. It is in the second quadrant. 5 pi thirds is about right here. It's a nice angle. Okay, so let's first start by evaluating sine squared of theta. That's how you read this. You call it sine squared. However, when we have this little 2 up here, that is just notation. All this is saying is to find the sine of theta and then square it. You don't have to do anything fancy with the theta. We ignore the squared until we are done evaluating the sine of theta, which we can do this. We want the sine of pi thirds, or 5 pi thirds, and then we want to square it. We could use our reference angle here of pi thirds if we wanted to. We could also just think about, if you have the entire circle memorized, what the sine of 5 pi thirds is. In this case, the sine of 5 pi thirds ends up being negative root 3 over 2. Or is it? I think it's negative root 3 over 2. No, wait. Hold on. No. It's positive 1/2. It's positive 1/2. Sine of 5 pi thirds is positive 1/2. And we want to square that. So the sine squared of theta is just 1 squared over 2 squared, because that's how we square fractions. We square the numerator and we square the denominator. And that gets us to 1/4. Okay, so let's think about this next one, cosine of negative theta over 2. This time we do have something in the argument, but we can deal with that. So we want to think about the cosine of negative theta over 2. All that is saying is we want the cosine of negative 5 pi thirds divided by 2. Negative 5 pi thirds divided by 2 is negative 5 pi sixths. You can verify that by doing some division with fractions. And when we're done with that, we get the cosine of negative 5 pi sixths is negative root 3 over 2. Okay, I actually realized I messed up here. This angle is not 5 pi thirds. This angle is 5 pi sixths. I got ahead of myself because pi is here. 5 pi thirds is actually in this quadrant down here, which is why I was thinking about the wrong angle up here. I am so sorry. I'm gonna do this one over again. Sine of 5 pi thirds actually does happen to be negative root 3 over 2. I am so sorry, because this is that angle down here. It doesn't make sense that 5 pi thirds would be in the second quadrant because it's greater than pi. So negative root 3 over 2 squared, we want to square the numerator and the denominator. Negative root 3 squared is 3, 2 squared is 4. This answer down here is still correct. However, this one was not. I'm sorry. Okay, now that that's straightened up, let's think of 3 times the tangent of 2 theta. All this is saying is I'm going to leave this 3 alone on the outside, and then I'm going to multiply it by whatever the tangent of 2 times 5 pi thirds is, which, just doing a little arithmetic, is the same as 3 times the tangent of 10 pi thirds. Here, it may be easiest to think of a reference angle, or if we want to make our lives a little simpler right now, we can just find a coterminal angle by subtracting multiples of 2 pi off. And how do we, 2 pi is just the same as 6 pi over 3. I just multiplied 2 pi by 3 in both the numerator and denominator because I wanted a common denominator for subtraction. That gets us to 3 times the tangent of 4 pi thirds. 4 pi thirds, we go, this is 3 pi thirds, one more is 4 pi thirds, so we know 4 pi thirds is that angle down there. And from our unit circle, we know that this is 3 times the sine of 4 pi thirds over the cosine of 4 pi thirds, which is just 3 times the sine of 4 pi thirds from our unit circle is actually root 3 over 2, or negative root 3 over 2, and the cosine of 4 pi thirds is negative 1/2. So when we do that division, it is 3 times negative root 3 over 2 divided by negative 1/2. So it's negative root 3 over 2 times invert and multiply negative 2 over 1. The 2's cancel and the negative signs cancel, so we're just left with square root of 3. So this is just 3 times the square root of 3. So your final answer is 3 root 3. Are there any questions on this slide at all? This is just to show that we can do different arithmetic with sine, cosine, and tangent. We can square our answer, but we don't do that till after we've evaluated the function. We can also have things in the argument, like we can have factors that we multiply or divide our theta by before we evaluate, and then we can have some constant coefficient we multiply by after. There's a lot of different things we can do with these. Okay, well, if there's no questions, let's do a very quick example. This one looks scary at first. I promise it's not as bad as it looks. So the maximum height of a function is given by h equals v naught squared sine squared theta over 2g. This looks complicated. You don't need to understand where it comes from. It's a physics thing. Just know that you're given this. And what these values mean, v naught, I say naught, it usually means if we have a 0 and a subscript, it's oftentimes called naught. It's the initial velocity. G is 9.8 meters per second squared. And if you've ever taken a physics class, you know that this is just the value for gravity. It doesn't change. It's Earth's gravity. And theta is the angle with which the object was launched from. Use a calculator to find the maximum height. So the maximum height being h, because that's what the formula is for. If the initial velocity was 90 meters per second and the angle was 1.83 radians. Okay, so initial velocity being 90 meters per second, that means we're given our v naught value. It's just 90 meters per second. And the angle is 1.83 radians. Well, that's our theta. And now we have v naught in this equation. We have our v naught, we have theta, and we have g. The only unknown we have left is h. All this is just interpreting the data and plugging it into our equation. So let's do that. We know that h is equal to v naught squared. V naught is 90, so it's 90 squared times the sine squared of theta. And if you remember, sine squared of theta is just the sine of theta squared. So it's the sine of 1.83 quantity squared. You don't square the 1.83, you square it after you evaluate the sine function. And then divided by 2 times g, which is always 9.8. I could do this out and simplify it more, but I have all the numbers I need, so I can just plug this into my calculator to get that it is 386.12. Now we're finding a height, and we know that that gravity was given in meters per second, our initial velocity was given in meters per second, so this height is going to be in meters. You could confirm this by keeping track of the units. If you use that 9.8 was meters per second squared down here, and if you use that the 90 was in meters per second, you could keep track of those units. However, you can intuitively just look and say, okay, I'm looking for a height. That is going to be a distance. It is probably in meters. Any questions on this? These kinds of problems are just a matter of interpretation, organizing the data. What do you know? What do you have? What do you want to solve for? And then it's, high school algebra of you have an equation with one unknown and you're solving for that unknown. In this case, it was really easy because it was the unknown that was already by itself and you just had to plug stuff in. But okay, how much time? Okay, we have 15 minutes. Okay, we have 15 minutes, so I'm going to just briefly start on what our next topic will be, and that will be graphing these things. We've been doing some kind of graphs with like these pictures here and drawing a graph every time, but it turns out just like with quadratics and polynomials and logarithms and all that fun stuff, sine functions also have graphs too in the same sense on an axis. So you can ignore this part because you do not have your course packets yet. They're still not in the bookstore. I don't know what's going on. I will probably be calling them after class, by the way, and I will let you guys know what's going on. But ignore that for now. I will just talk us through how we're going to do this. But okay, so when we're doing this graph, if you think about other graphs, we have an input X and then an output Y. Same thing here. We're going to put some value into our sine function, something we're calling X, and it's going to spit out the sine of X, and that's what we're going to plot. The X-axis here is going to be the X values, and the Y-axis here is going to be the sine of X values. X in this case, we're used to X just being a coordinate. In this case, X is the same as theta. X is our angle theta that we are plugging in. You can think about it as an angle because that's how we've been thinking about it up to this point. And then whatever its sine is going to be the output, or what we can traditionally consider the Y value of the equation. So let's start by plotting some of these points just to see what's going on. When we plug in 0, we get 0. Makes sense. The sine of 0 is 0. You can confirm this on the unit circle. Pi 6, the sine of pi 6 is 1/2. So we can sketch that in. Pi fourths, the sine of pi fourths is the square root of 2/2. Pi thirds, the sine of that is square root of 3/2. And pi halves, the sine of that is 1. So we can already see we're starting to get this sort of curvy shape here. And that kind of makes sense, right? If we think about our unit circle, think about that. We start, just draw these axes a little bit. Here's pi halves, radians, here's pi, here's 3 pi halves, here's 2 pi. So when we start at 0 here, the sine, the Y values are going up first at a very fast rate and then leveling off until they hit 1 there. That's the unit circle because the sine of pi halves is 1. This point right here is 0, 1. So it makes sense that our sine values are going to go up very, very, very sharply and level off until they're at 1. Okay, so I will highlight that in red too, just so we can keep track of what's happening. Now let's keep going a little bit. Think about the sine of 3 pi fourths. That is also root 2/2. So we're going, oopsies, we're going back down a little bit. Sine of 3 pi fourths is just root 2/2. And then the sine of pi, we're back down to 0, which makes sense because the Y value at pi is 0. We are sitting on the X-axis. It is an X-intercept, so the sine will be 0 when we do that. So it makes sense that the curve will go back down like this because those y values on the unit circle are also just going back down. So this part of the circle here is this part of the graph. Okay, and now, as you can see on this part of the circle here, our values are going negative. We're going to start having negative y values, which again lines up with the sine function when you plug it in. The sine of pi fourths, which is an angle that's down here somewhere, is negative root 2 over 2. So we'll be down here. And then the sine of 3 pi halves is negative 1. So we're doing kind of the exact same shape, just now down into the negative part of the graph. That is that part of the circle. And then as we'd expect, the y values start to go up again here. We're starting to get back to positive and we're working our way back to 0, which is exactly what happens when we plot this out. Negative 7 pi fourths is negative root 2 over, or 7 pi fourths is negative root 2 over 2. And then the sine of 2 pi is 0. So we're working our way back up. So it makes sense that is this part of the circle. And this cycle will repeat because we're just going to keep going around the same circle. And you can think about the y values are going to keep varying this way. So in that way, the y values, the values of sine actually continue in this exact same manner when we start to think about negative angles. The sine of negative pi fourths happens to be negative root 2 over 2. The sine of negative pi halves is negative 1. 3 pi fourths is negative root 2 over 2, 0, etc., etc. It will keep going in this manner pretty much forever because you're going to keep looping around the exact same circle. So your graph will look like this. Come on. And it will continue like that forever and ever. Okay. What we're going to really focus on here, though, is this part of the graph. I'm going to draw a box around it for reasons I will explain later, but this is called the principal part of the graph. It is one cycle of the graph. It is one cycle of sine. So you can think about this exact pattern will keep repeating like that forever and ever because that is one full rotation around the circle. This is called the parent graph of sine x. You may remember this from graph transformations in college algebra. We're going to manipulate this graph a lot, but this is called the parent graph. And this guy right here in the box, this principal part, will be extremely important for when we're thinking about graphing more complicated versions of this later. Okay, so let's start by doing not too difficult of an example of it, and then we will wrap up class for the day. So I want to sketch the graph of y equals the sine of x minus 1. Identify the amplitude and vertical shift. So those are some words we haven't heard of, so I'm just going to define them real quick. Amplitude refers to the amplitude of a wave, which makes sense because when we look at this graph up here, it's pretty clear that the sine graph is going to be some kind of repeating wave. So the amplitude of the wave is the distance between the top part and the middle, or the midpoint of the wave. So for the basic sine graph, here would be the top point right here, and here is the midpoint it intersects. So it goes from 0 to 1, therefore the amplitude of the parent graph of sine x is 1. Now the vertical shift is pretty self-explanatory. It is just how much the graph is shifted up or down. You've probably seen vertical shifts with pretty much any other kind of graph you've made before: linear, quadratics, polynomials, logarithms, exponentials, et cetera, et cetera. You've probably talked about vertical shifts before. So just to give us a baseline, I'm going to sketch the parent graph of sine again right here. We know that this is what it looks like from the previous slide. And I'm just one by one going to add these two little pieces of transformation on. First, I want to deal with the amplitude, and the amplitude is changed by this guy right here. We're going to multiply every single one of our output values by 2 instead of the sine of x. It's the sine of x times 2. So every single value on this graph for 2 sine x is doubled. So instead of our high point being 1, our high point is 2. So our new amplitude is 2 because everything is multiplied by 2. So we have this, this, and this. So this purple graph right here represents 2 sine x. The last thing we need to do is every single one of these values, we then take 1 away from. So the vertical shift is -1. We're just moving everything down by 1. So I think I will draw that graph over on these axes over here, and that will be our final answer. So instead of starting at 0, which we did over here, we need to move that down 1 because we're moving everything down 1. Okay, now at pi halves, we hit 2 on the other graph, but we're shifting everything down by 1, so now it's going to be a 1. At pi, we hit 0, but we need to shift that down 1 again. At 3 pi halves, we hit -2, but we need to shift that down 1, so it's at -3. Oopsies, etc., etc. So the graph will look like this. That is what the final graph 2 sine of x minus 1 is, but we're given more axes, and we know that sine goes on forever, so we need to continue this graph in the negative way in the exact same fashion. We know it will continue like that. Any questions on how I work through this? This is not the process you will use every time. We will do that next class, I believe. Yep, that is what we will start with next class, is the general process you'll be able to use for all of these. This is just to help you gain some intuition for how these work, what we have to be thinking about, and intuitively what these two numbers are doing. Are there any questions? Okay, I think this is a great stopping place for today then, because the next time we're going to really get into the meat of how to graph these, what they look like, and introducing some other parent functions like cosine, tangent, etc. But for now, I think this is a fantastic place to stop. Don't forget, you have your ALEX due tonight, as well as a written homework due tomorrow. I have office hours right now, so if anyone needs help, I will stick around. Otherwise, I hope you have a fabulous Thursday, and I will see you all tomorrow.